So you're rewriting and taking these derivatives. So either expanding or using an identity to rewrite so that you can take these derivatives, and then you're looking for a pattern, maybe a shortcut when we get to the end. So several of you are finishing. Once you're done, look at those answers. Do you see a pattern? Can you find a shortcut that would allow you to have done the derivative and gotten the same answer, maybe in a little bit different way? That's what we want to look for. All of these are similar in that they are function composition. We've been learning some derivative shortcuts to help us take derivatives a little more efficiently, but we've dealt with functions that are just individual functions added, subtracted, multiplied, and divided. But we have a fifth way to create functions, and that's by composing functions together, which might be, in all honesty, the most common way that functions happen in real life. And that's what we have in each of these. We're going to take each of the little problems that you've done here, and maybe to help you look for a pattern, we're going to rewrite our derivatives. There is nothing wrong with our answers, okay? So we'll go through, we'll check your answers, make sure we're comfortable with those, but then we're going to do a little rewriting to see if we can notice a pattern. In the first three problems, all of those I can just expand. I can multiply out. I can rewrite y before I go and find the derivative. And each of those then just means I'm using my power rule. Okay? The derivative, for example, of 9x squared is 18x. The derivative of 30x is 30, and the derivative of 25 is just 0. Are there any questions in getting the derivative in 1, 2, or 3? Okay, in 4 and 5, you have a little trig. In number 4, sine squared means sine times sine, so we can use the product rule. The first times the derivative of the second, plus the second times the derivative of the first. And we worked last week on the derivative of sine, which is just cosine. So we have 2 sine x cosine x. Now in number 5, we've really started to try to talk about this idea of, before you get so excited to take the derivative, to see, can I rewrite this? And we can use an identity. We can rewrite sine of 2x as 2 sine x cosine x. And this is a product. So we can use our product rule. The first times the derivative of the second, plus the second times the derivative of the first. The derivative of cosine is negative sine, so we have negative 2 sine squared x. And then the derivative of 2 sine x is 2 cosine x, and so we have plus 2 cosine squared x. And then number 6, again, we can expand. So x to the 4th plus 3 squared is x to the 8th plus 6x to the 4th plus 9. And its derivative, just using our power rule, we get 8x to the 7th plus 24x cubed plus 0. Now, are there questions there in 4, 5, or 6? All right. So similar things in 7, 8, 9, and 10. In 7, we can expand. In 8, we can write cosine squared as cosine times cosine and use our product rule. And then in number 9, you might find it helpful to write this as x to the 1/3 plus 3 quantity squared to help you with your expanding. So x to the 2/3 plus 6x to the 1/3 plus 9. And so our derivative is, again, just there, our power rule. 2/3 x to the negative 1/3 plus 2x to the negative 2/3. Now, questions in the derivative in 7, 8, or 9? All right, and then your last one, again, you could do by expanding. We can rewrite this before we take the derivative. We get x to the 4th minus 8x squared plus 16. And the derivative is 4x cubed minus 16x. Now, what I tried to do with these 10 problems was giving you 10 things that had function composition that you could find the derivative because it was simple function composition. And what we want to look for is a pattern. So I'm going to take, and we're going to start to rewrite these derivatives Now, there's nothing wrong with our answers, but I think if you didn't see a pattern, it may help you to do a little rewriting. So 18x minus 30, we've got a greatest common factor. Let's plus out our 6 here. So you have 6 times 3x minus 5. Or even better, it might be helpful for you, we have 2 times 3x minus 5 times 3. 2 times 3 gives us 6. Now I'm going to write the times 3 out here on the end, and there's a reason for that to try to help you to see a pattern. All right, let's go to number 2. So we're going to try to rewrite as many of these as we can. See if it helps you to recognize a pattern. So number 2, we got a greatest common factor. We've got a greatest common factor of 6x squared. So 6x squared times x cubed, and 6x squared times 4. Or we could write our derivative here as 2 times x cubed plus 4 times 3x squared. 2 times 3x squared gives us the 6x squared. Now you might look at number 3 and say, well, I can't rewrite that. But when you were 9th and 10th grade, you worked on factoring things that had negative exponents. That really just means we're looking for a common denominator, which in this case, our common denominator is x to the negative 1/2. So times x to the 1/2, or the square root of x, plus 5. Now, this last one, I'm going to be a little creative in how I finish rewriting. We aren't going to change the problem, but I'm going to write this as 2 times 1/2. So that's still 1. And then x to the negative 1/2. And then here, in place of x to the 1/2, I'm going to write square root of x. But the 2 times 1/2 is to try to help you see a little pattern. All right, let's go on down, see what we can do rewriting as we keep going. Not really much I can do. You could write this 2 sine x cosine x as the sine of 2x. I actually don't think that will help you to see a pattern. It is correct. All I'm going to do is put a times in here so we don't have just implied multiplication. You can actually see the multiplication there. I think that might help us when we're all done looking for our pattern. I can factor here in number 5. So I'm going to factor. So dy dx. I'm going to factor out this negative 2. And I prefer to write my positive piece first. So hang on. Let's just factor out a 2. So 2 times cosine squared x minus sine squared x. Now that is an identity. 2 cosine of 2x, or 2 times the cosine of 2x. Now similarly here, number 6, we can rewrite. We've got a little factoring we can do. We have a greatest common factor here of 8x to the 3rd. That leaves us with x to the 4th plus 3. Or 2 times x to the 4th plus 3 times 2 times 4 gives us 8. 2 times 4x cubed. Again, this is just to try to help us to see a pattern. All right, number 7, we got a derivative of 8x minus 4, or we might just say, well, that has a greatest common factor of 4. 4 times 2x minus 1, which is 2 times 2. 2 times 2x minus 1 times 2. So cosine squared, I'm just going to put a dot here for our multiplication. This is negative 2 sine of 2x, okay, 2 sine x cosine x, but I think that will make the pattern harder for you to see. In number 9, we can factor out a greatest common factor here. So We're going to factor out here an x to the 2/3, excuse me. X to the negative 2/3. So that leaves us, let's actually do it this way. I think this will be easier for you to see. That is the best way to factor it, but I think it'll be more helpful if we pull out a 2/3 x to the negative 1/3. I think that will be more helpful for you. So then it looks like we've got, okay, plus 1, or times 1, plus 3 x to the negative 1/3. Okay. So we'll pull out another x to the negative 1/3 here. 2/3 x to the negative 2/3 times x to the 1/3 plus 3. Well, let's write that as a cube root. So 2 times the cube root of x plus 3 times 1/3. 2 times a third gives us 2/3. X to the negative 2/3. And then our very last one. We got a greatest common factor here of 4x. That leaves us with x squared minus 4. But let's write that as 2 times 2x. And what I want you to do is I want you to look at all of those pieces, and we want to look for a pattern. Okay? Is there anything you notice? Now, I know as I zoom out, you aren't really going to be able to see all those, but I want you to be looking at all of those problems put together. Do you notice any patterns? So let me give you just a moment to look, and then we'll let you. All right, now the first three are a great place to see a pattern for this derivative of function composition. Anybody notice a pattern in those three problems? So share and speak up. So one of the things we notice is, okay, this piece, the stuff inside our parentheses, is what was in our original problem that was being squared. Okay, that's true in all of those. It's even true down here in our sine squared, the part that was being squared. There it is. Well, where does 2 come from? What does that look like? That 2 is our exponent. So wait a minute. This part looks a lot like that's just my power rule. I've got something squared. Bring the power down in front. Decrease by 1. Bring the power down in front. Decrease by 1. Bring the power down in front. Decrease by 1. I mean, it kind of looks like I just took the derivative of that. Bring the power down in front. Decrease by 1. I mean, we don't write an exponent of 1 there. Okay. Well, what about this last piece? I mean, where did that thing come from? What is that? Okay, so it does, these are a little tricky. They look like they're the derivative just of this first piece. They're actually not. It's actually the derivative of this whole thing. But you don't see a second piece because -5, +4, and +5 are all constants. Okay? And the derivative of constants is 0. Well, now wait a minute. Did that still work in number 4? The derivative of what I had, well, yeah, because the derivative of what's on the inside, if I think of this as sine of x squared, well, there's my power rule. Bring the power down in front, decrease by 1, and the derivative of sine is cosine. But I don't have exponents in number 5, so surely that's not the same pattern. We'll look at it. Now I'm going to write parentheses here so you can see your function composition. It's exactly the same thing. We have the derivative of this function, sine. There it is, cosine. And then the derivative of the piece inside our parentheses. That's our 2. And so what you all are noticing in these 10 problems is what we call the chain rule. It is, without a doubt, the most important derivative shortcut we'll do all year long. And so we're going to use problem number 2, right, to make sure we understand how we take the derivative, the slope of function composition. Okay? So you all took this problem and you found the derivative. Right? You multiplied out to expand function y, and you got the derivative was 6x to the 5th plus 24x squared. And we looked at, we could write this derivative by factoring out the greatest common factor. And then we even rewrote this as 2 times 3x squared. And it's that form I want us to look at. Because this exhibits our chain rule. Now, we're going to look at this function as actual function composition, as f of g of x. So in that case, we've got, let's think of this as an outside function, something squared, and then our inside function, x cubed plus 4. And we've composed those together, f of g of x. Now, we got our derivative of f of g of x was 2 times x cubed plus 4 times 3x squared, or 6x squared times x cubed plus 4. And I want to look at that. Well, how does that compare to this function composition? Right? Well, you all notice the pattern. We just took the derivative of the outside function. The derivative of something squared, 2 times something to the first power, times the derivative of our inside function. Now, it was hard to see that we actually took the derivative of the whole inside because the plus 4 was equal to 0. We actually call this differentiation by products. We're multiplying together to get this derivative. So if we write this in function notation, right, well, we had that f of x was x squared. We took that derivative, bring the power down in front, decrease by 1. That would be f prime. But we didn't evaluate it at x, we evaluated it at function g, our inner function. And then we took the derivative of the inside piece. This is our chain rule. This is the exact pattern you all noticed. The derivative of the outside times the derivative of the inside. That's the chain rule. And it's a very, very important, powerful way to take the derivative when we put functions together. So let's illustrate that with our exact pattern. So let's take problem number 1 here. We're going to rewrite it as function composition. So f of x would be something squared, x squared. G of x would be 3x minus 5. So if we want the derivative of f of g of x, we're going to start on the outside. That's something squared. The derivative of something squared is 2 times that something to the first power. And I'm going to write that so we can see our power rule. Evaluated at function g, so 3x minus 5, times the derivative of our inside piece. So the derivative of g of x. So the derivative with respect to x of 3x minus 5. And the derivative of 3x minus 5 is going to be 3. And that's what we did in all 10 of those problems. That's our chain rule. The derivative of the outside times the derivative of the inside. Now, before we practice this a little bit, are there any questions about that pattern? All right. Then before we practice, I want to look at this chain rule using a second notation. Now, we wrote this with function composition, right, using our function notation, f of g of x. But we can also write this notationally in a different way, but we have the same pattern. So when you were in 9th and 10th grade, especially sometimes with some factoring problems, you would take and you would do a substitution, typically a u substitution, to rewrite a complicated expression. Now, while x cubed plus 4 quantity squared is not this overly complicated expression, right, we can rewrite this using a u substitution. Right? We can let u be x cubed plus 4, and we just then have the function y equals u squared. And we're going to do the little pattern that you all noticed. Right? We're going to take the derivative of the outside, and we have here for the first time a derivative with respect to something besides x. We have the derivative, take the derivative of y with respect to u. Well, that's just our power rule. The derivative of u squared is 2u. And then we have our inside function, the derivative of u with respect to x. So the derivative of x cubed is 3x squared, and the derivative of 4 is 0. Okay? So I'm going to write plus 0 to make sure we can see we took the derivative of that whole thing. And what I want you to notice here is that we already know this derivative, right? We've already taken it. The derivative dy dx turned out to be 2 times x cubed plus 4 times 3x squared. Well, how do we get that using this u notation and just slope notation? Well, look at here. This is dy du. That's 2u. The derivative of the outside times the derivative of the inside, du dx. And we have the same exact pattern, differentiation by products, the derivative of the outside times the derivative of the inside. If I could spell differentiation today. But there's something really important to note in this notation. It's not a different pattern, but something you might not have thought of. I really can't spell today. When you write Leibniz notation, when we write Leibniz notation, we're writing fractions because this is the change in y, the instantaneous change in y. The instantaneous change in u, the instantaneous change in u, the instantaneous change in x. But what you might notice that it looks like is we're getting dy dx. It looks like these are just dividing out, and that's exactly what's happening. Those differentials are dividing out. And so it, for the first time, allows you maybe to really see a reason why this Leibniz notation that just looks like a fraction is useful. When we recognize that this is an operator, we can use things that we're used to with operators. We can multiply, we can divide, we can kind of see that happening. So what we're going to do is we're going to go back to those 10 problems. And we're going to start to look at least with a couple of those. We won't get through all 10 of them using this new shortcut. And we'll write some of them with function composition. So f of g of x, and take our derivative. And some of them with Leibniz notation to see we're doing the same thing. The derivative of the outside times the derivative of the inside. So dy dx, the derivative of the outside part, the derivative of something squared, bring our power down in front, decrease by 1. And then take the derivative of the inside piece. Now, it is going to be a requirement for quite some time that we write this derivative of the inside piece. We write out that we're going to do that. Part of that is for problems that get more complicated. The other part is this is the most commonly easily missed part when we do our chain rule. And you're going to hear me lots of times when you miss this go, chain rule, because you miss the derivative of the inside piece. And we get our derivative, 2 times x cubed plus 4 times 3x squared. The derivative of the outside times the derivative of the inside. That's our chain rule pattern. Now, are there any questions there with number 2? Okay, number 3, we're going to write using Leibniz notation. We're going to let u be the square root of x plus 5. And so y is u squared. So dy, the derivative of y with respect to x, would be dy du, the derivative of y with respect to u, times du dx. So the du's divide out, they cancel out, and we get dy dx. So the derivative of y with respect to u is 2u. The derivative of x is 1/2 x to the negative 1/2 plus 0. We're not going to write plus 0. So 2, in place of u, we'll put what u is, times 1/2 x to the negative 1/2. And notice, this is the derivative of the outside part. That's our power rule. And here's the derivative of our inside part. The derivative of the square root of x plus 5. That's our chain rule. Right? So that if we have 2 differentiable functions, f and g, that we are composing together, do remember, differentiability would also imply these are continuous. Okay, differentiability implies continuity. And we compose those together, then that composition is going to be differentiable. The derivative of the outside times the derivative of the inside. And if you understand this pattern, it won't matter how complicated the functions get. We can take the derivative using the derivative of the outside times the derivative of the inside. Are there questions with this brand new, really important shortcut called the chain rule? All right. Then let's look at a really, really good little example. The sine of, the cosine of x cubed plus 3. This is a function composition problem. So there's our y. Now, if we understand this chain rule, even though this looks like it's a whole lot harder, actually, let's do this. Let's make it sine to the 4th. Now it looks really, really hard. It's not. It might be helpful for us to write it in a little different way to take the derivative. So I'm going to write this as sine to the 4th, so it's a little easier to see our function composition there. But this is just function composition. So the derivative, dy dx, is going to be, all right, let's take the derivative of the outside piece. Well, the outside piece is something to the 4th power. That derivative is 4 times something to the 3rd power. And that something is our function g, the sine of the cosine of x cubed plus 3. The derivative of our outside piece times the derivative of our inside piece. So our inside piece in this case is the sine of the cosine of x cubed plus 3. Now, the reason this looked like it was going to be this really, really hard problem when we start is because this inside piece is function composition. So the inside piece is going to have chain rule in it. But if I understand chain rule, I don't have any trouble with this. I can do this as much as you want. So 4 sine cubed cosine x cubed plus 3. And then we're going to do our chain rule. Treat this as a brand new problem. Okay? So the derivative of the outside, well, that's the derivative of sine. The derivative of sine is cosine. Evaluated at our inside. So cosine of x cubed plus 3 times the derivative of our inside piece. So our inside piece is cosine of x cubed plus 3. This is still function composition on our inside. So we have 4 sine cubed of the cosine of x cubed plus 3 times the cosine of the cosine of x cubed plus 3 times, okay, so we're going to do our chain rule. We're going to start on the outside. So the derivative of cosine, that's negative sine, evaluated at our inside piece, times the derivative of the inside. So the derivative of x cubed plus 3. Now, that piece, we don't have function composition, so we're almost done. 4 sine cubed of the cosine of x cubed plus 3 times the cosine of the cosine of x cubed plus 3. And I'm going to put our negative out here. Times the sine of x cubed plus 3 times the derivative of x cubed is 3x squared, and the derivative of 3 is 0. And so yes, we could call this negative 12x squared, but we just kept repeating the chain rules. Start on the outside times the derivative of the inside. Start on the outside times the derivative of the inside. That's the pattern, right, that you all noticed in those first 10 problems. That's our chain rule. Okay? Now, for tonight, I have two things I want you to do for me. The first, you already have the answer to these first 10 problems. Okay? But I want you to go back just like what we did with the first 3, and I want you to try them using this chain rule. Okay? And then the second piece, your homework is you've got Math Calculus Math Notebook number 8 in Math Excel, okay, to complete. All right. Tomorrow we'll meet again virtually. We will work some more on chain rule tomorrow. And I will be back on Wednesday. I'll see you all then on face-to-face again on Friday for your exam. All right, guys, have a great day.